Okay, so the first thing is let's compute the reaction forces at A and B. Without that, we cannot draw the shear force and bending moment diagram. So step one, let's draw a free body diagram. So replace the effect of the pin joint here at A with vertical force and a horizontal force. Replace the effect of the roller with a vertical force only. Okay, now we have 20 kilonewton force. We have a moment 150 kilonewton meter. And now we also have a new force here, the distributed load. Now, the way we would like to, well, what this force really means is it acts, it's denoted as force per unit length. So if you want to find the magnitude of the force over the complete length over which it's applied, applied over 8 meters, this force will effectively, this distributed load will effectively produce a net force of 8 times 40, which is about 320 kilonewtons. And we also need where exactly this force acts. So we can replace this distributed load with a point load acting at, assuming it's uniformly distributed, exactly midway of that load. So the midway of this, the midway of 8 meters is 4. So we can assume that this force is applied. It's 40 times 4, sorry, 40 times 8, 320, and it acts exactly midway. And I need to do that in order to draw the free body diagram. 4, 4, and 3. Okay, this simplification is only good for the reaction forces. This simplification of putting it as a point load will not work when you draw the shear force and bending moment diagram. We'll have to retain the distributed load when we do those. Okay, so next, the coordinate frame. Up is y, right is x. That's step 2. And step 3 is write the equations of equilibrium. It's not too hard to see that Fx, which is there's only one force, HA, is equal to 0. Fy is equal to 0. So that we'll write Va upwards is positive, 320 is downwards negative, 20 is downwards negative, and Vb is upward positive. So that gives me Va plus Vb equals 340. Now there's a 150 kilonewton meter moment, which is a moment and it will not appear in the force. Finally, we can take moments about any point. We can take about A or B. Let's just take it about A like we always have done here. So now we can write the moments due to individual loads. We have 320, which is now is like almost like a point load acting at a distance of 4 meters from A. So 4. This 320 acting at 4 meters will induce a clockwise moment. So I'll put a negative sign. Then we have VB acting at a distance of 8 meters from A. That will induce a counterclockwise moment about A. So that would be positive. Then we have 20 kilonewtons acting at a distance of 4 plus 4 plus 3, that's 11. That induces a clockwise moment, so negative. And then the 150 is already, well, it's acting in the clockwise direction it's shown, so it's going to be minus 150. All this equals 0. Okay, so I computed this offline. It comes out to be 206.25 kilonewton. Let's call this 2, 1, 3, substitute PP is equal to 206.25 into and solve for so doing that gives us VA equals it's going to be 340 minus 206.25 comes out to be 133.75 kilonewtons. Okay, now let's go to the next step, which is shear force bending moment diagram. Since this involves a distributed load, and I've not solved any problem on that, I'll try to solve it both methods so you can see, you can compare the two. Okay, so let's do it with the first method, which is writing all those equations. Okay, so I'm going to draw the shear force diagram first. Let's redraw the free body diagram with all the unknowns now are known. So we have 133.75. You have 206.75, so 25. Okay, now here's where you need to show the distributed load. You just cannot write it as uh, a point load like I showed in the free body diagram earlier. So I have to draw it this way, otherwise I won't get the right answer. So this is 40 kilonewton per meter. And then we have 20, then we have 150 kilonewton meter moment. Okay, let's name them. Let's call this A, let's call this B, and then we just need this point C. Okay, now this case we have, well, we have the distributed load. So what we'll do is we'll cut a section between A and B, write the equations. Thankfully, B, the force at B, the reaction force ends as well as the uniform distributed load ends at the same point. So that saves us from drawing a diagram for that. If this reaction force ended right here, then we'll have to make another cut here, write the equation and so on. So, but in this case, we are lucky that this force ends exactly at B. So we only need to draw two diagrams, not three, like the previous one between A and B by putting a cut, and one between B and C by putting a cut there. So let's do the first one. A. So we put a cut right there. We have X, 133.75, 40, and that's about it. And so again, our convention when we go from left to right is that downwards is positive. So we have plus V minus 133.75, and then the 40 is a distributed load. It's the net force is obviously downward direction, so it's going to be positive. But the net, since this is 14 kilonewton per meter, and it's for a stretch of x meters, so we'll have 40 times x is the net force. So this is the net force. Okay, so all this should be equal to 0. This gives us a formula for V. It is 133.75 minus 40x, and this formula is varied from x equals 0. Remember, this was 8. So it's valid from 0 all the way to 8. Okay, next we draw, well, we cut the beam between B and C and then show all the forces, 33.75. It's A. We have B, 206.25. It's equation 40x. Yes, correct. 40x. Thanks for correcting me. Okay, one. So this is the cut. And so then again, when we look at the distance, this will always be up till the point where we put the cut x. Okay, so again, V is downwards. Uh, let's write the equation. So plus V is downwards because downwards is positive. 133.75 is upwards. 206.25 is upwards, so negative. And then this 40 now is, well, it's at a distance. This is 8 meters. And this force is 40. So here, the complete load due to that 40 kilonewton acting over 8 meters will show up. So we have 40 times 8. And remember, it's acting downwards, so it's positive. That should be equal to 0. Yes, so when we do the math, comes out to be, should come out to 20 or minus 20 probably. It comes out to be 20. It's a constant. Okay, so with that, we can draw the shear force diagram. We need two equations. First equation is this. Second equation is this. And the region of validity for this equation is between 8 and 11. So here is the shear force diagram. V is a function of x. Okay, so we have, we need to put some values here. Let's put x equals 0, which is the point A. So we have V equals 133.75. So it starts off at 133.75. So that's 1 point. Now, when you put x equals 8, we have 133.75 minus 40 times 8, so minus 320. So at B we have 186.25. How did I get it? Well, this is the calculation. This is equal to 133.75 minus 40 times 8. Okay, so that gives us another point. This is 1 point. Okay, now we need to connect the dots. We need to connect A with B. For that, we need to look at the equation. We have V is a function of x. It's a linear function of x. So it's a straight line which connects A and B. So all we do is draw a straight line. That's it. Okay, then what happens is at B, we have V equals 20. That's a constant force. So we'll have at 8, again, we have 20. And then this 20 will keep going all the way to 11. So C. Okay, so this force, interestingly, abruptly changes from being 186.25 all the way to 20. And the reason is because of the reaction force. Because of this 206.25, we see that the force goes from minus 186 to 20. In fact, if you add, well, if you do 186.25 minus 20, you'll have exactly the reaction force at B. So this is our shear force diagram. Okay, now one of the curiosities is, what is this point? when does the shear force become equal to 0? In order to compute that, what we can do is we already have access to the formula. We know that the formula for v as a function of x between 0 and 8 is this. So if we want to compute that point, all we need to do is substitute v equals 0 and compute x. So if you put v equals 0, 133.75 minus 40 times x, solve for x, what I get is 3.43. So this point is 3.43. Okay, this will actually be needed for the second method, because you can see that on the left side, the area under the curve is positive, on the right is negative, and without that computation, we can't use um, the other method, which we'll talk in just a bit. Okay, so that's the shear force diagram. Let's draw the bending moment diagram. Okay, like the previous case, we only need to consider two sections, uh, one between A and B, another between B and C. So let's do that. This is A, 133.75, put a moment M, and then the distributed force. So we need to write an equation for M. So we always take moments about the point where we put the cut. And this is 40, and of course this is X. Okay, so we can write 133.75 times x. So this is the moment due to the reaction force at A, and that's acting in the clockwise direction. Our convention is clockwise is negative. Then we have 40 times x. So this is the net force due to the 40 kilonewton per meter distributed force. But that force will be acting approximately midway, right? So the distance of the point of this load, the net force, is x divided by 2 from the point at which we put the cut. So it's x divided by 2. This is the momentum. Okay, and then this one would induce as you can see, it's downward, so it induce a counterclockwise moment, so it's plus, and then m is counterclockwise, so plus equals 0. Hey, so we can simplify m, comes out to be x times 133.75 minus 20x. And that's true for our x from 0 to 8. Okay, let's draw a free body diagram with a cut between B and C. 133.75, 206.25. Okay. It extends a little bit. Okay, so this point is where we'll apply the moment m. Let's write the equation. So we have 40. Okay, so 133.75. Okay, at a distance of, well, we have x here, and then this distance between A and B is 8. So let's write 133.75 at distance of x. It's going to induce a clockwise moment, so negative. Then we have the 40 uh, kilonewton force. It's basically force times the distance. So sorry, force times the length over which that 40 kilonewton per meter acts. So it's 8. The distance of the load, which is approximately midway, so it's 4 meters from, let's say from this point, from B is 4 meters. So this 4 plus this, so it's 4 here, 4 and 4. So the point of application, which is approximately midway, is at a distance of x minus 4. In other words, this distance is x minus 4. X minus 4. And so it's going to produce a counterclockwise moment. Okay, then we have B. It's 206.25. It's at a distance of x minus 8. It's going to induce a clockwise moment. And then we have M, which is counterclockwise. So all this equals 0. So from this, we can solve for M. The equation for M actually turns out to be pretty simple. It's 20 x minus 370. Okay, so with that, we can now draw the bending moment diagram. Okay, let's look at the first equation. This equation, the first one, is valid from 0 to 8. We put x equals 0, so we see that this 0 is 1 point at A. Then if you put at B, says B is here. So if you put x equals 8, for this point, we'll have to put x equals 8. So we have 8 times 133.75 minus 20 times 8. Okay, if you do that, I get minus 210, so it's actually negative. Okay, so we have minus 210 there. Now, we need to connect the dots between 0 and 8. So you see that the equation is actually quadratic. So it's a curve. Now the question is, how is this curve? Is it this way? Is it this way? Is it this way? Is it this way? Oh my God. This way, this way is not clear. So for that, what you need to do is you actually need to you need to plot at least one more point over here. You need to choose some value, x equals 4, and try to figure out where that point lies. It turns out that for this particular curve, for this particular equation, the curve looks like this. Okay, so to get this, need to subs some intermediate value. Okay. Okay, I'm almost done. I'm running out of time. The last step is to connect the dots from B to C. So for that, I put x equals, you can put x equals 8 first, and you'll see that x equals 8 is actually it's minus 210. Okay, so that point is right. And then if you put x equals 11, you get minus 150. So this here, we put x equals 11. And if you look at the equation between 8 and 11, it's a straight line. So all I need to do is join it by a straight line. So this is the bending moment diagram. Okay, so the idea here is to use the equations I wrote down. V equals dv dx equals q, and if q is minus w, where w being the load, and that's acting downward direction, then and this is a constant, by the way, right? Constant, because it's given, it's fixed. Now what we can do is we can do dv integral 1 to 2 integral minus w dx 1 to 2. So we have v2 minus v1 is minus to 1 w dx, and this is going to be something like x2 minus x1. In other words, what we observe is v is proportional to x, or it's linear in x. So when you draw the shear force diagram, you will see that it's not going to be a constant, it will be a straight line, either sloping up or down depending on the slope, depending on w. Yeah. V is the shear force. Uh, shear force. Distance. Yes, so that's one equation. The other equation we looked at last time was dm dx is v, and so in order to compute m, we can integrate this from 1 to 2. So it'll be m2 minus m1 equals, now if v is something like w wx, assume v is minus wx, that is comes from the first equation, then we can see that this will equate to something like w x square x2 square by 2 x1 square divided by 2. In other words, we'll see that the moment m is proportional to x square, it's quadratic, provided shear force is, well, there's a uniform loading w. So again, the moment, and then this is the distance. It's going to be squared. So this will be helpful when we figure out what is the type of curve which comes between 2 points. Is it going to be straight line? It's going to be a curve like a quadratic, and so on. With forces at A, VA, so that's 133.75. It's one of the forces we computed. There is the force at B, 206.25. There's a distributed load of 40 kilonewton per meter. And then at C, there is a downward force of 20, and then the moment of 150. These points are A, B, and C. And then to remind you, this distance is 8 meters, and this distance is 3 meters. So what we're going to do here is, as I said, we're going to use this equation and just straight off start drawing the shear force diagram. We don't really need to write any draw any free body diagrams. So V versus X. Okay, just straight from that equation. Okay, so first of all, when you start from the left side at A, we have 133.75. That's the shear force acting in the upward direction. So I'll show 133.75, which is this point. Okay, so I get that point. And now I need to draw the shear force due to this 40 kilonewton meter. Now, this is where I would use this dV dx equation. So let's use that. So we have dV dx equals minus 40. So I'm just going to rewrite it as dV equals minus 40 dx. When I integrate this, I integrate from say 1 to 2, 1 to 2. So I'll start from A, or 0 in this case, right? And then go to some other point V, okay, just to have a generic form. So we have from this equation V equals, well, my bad. So this is not 0, right? This should be what? 133.75. That's because at x equals 0, we have a force of we have a shear force of 133.75. So we have V minus 133.75 equals minus 40 times x. You could do that too. I just wanted to put it here, but yeah, you can do that. But you just have to be careful about the signs, if it's positive or negative, but yeah, absolutely you can do that. Okay, so that's basically showing how, and that's particularly true from x from what? 0 all the way to 8, right? 0 all the way to 8. So we cannot use this equation beyond 8. Okay, so you can check this equation. If you put x equals 0, it does give you V equals 133.75. That's one check as to this equation is right. Next, we need to compute the force, shear force at B. So we put x equals 8 and solve for solve for V. So V at B is equal to, so if you put that x equals 8, you get 186.25. Okay, which means that you now need to go at x equals 8, somewhere here, it's minus 186.25. Okay, so if you, since this is a linear function of x, we obviously need to connect these 2 points using a straight line. Okay. Now, one particular thing of interest is where exactly does this line intersect the x-axis? And that again can be obtained from the same equation. We need to compute x, where v is 0. So we put, so we need to compute this x. So what we do is we put v equals 0 minus 133.75 equals minus 40 times x. Here we're trying to solve for x. It turns out if you do this math, you get x equals 3.43, the same thing we got earlier. So this is 3.34. Okay, now that we are done with that part where the force was uniformly distributed, we no longer need to use that equation. If you want, you can use it, but it's essentially dV dx equals 0 because there's no uniform load from B all the way to C. So you may just use that. You don't have to really use it. What you'll do here from B to C is you see that there's 206.25 acting at B. So this will push the force from 186 plus 20.25. You'll add 206.25 to get 20. How did I get this? It's 186 point, sorry, minus 186.25 added to that 206.25. Okay, and thereafter from B to C, it all remains 20 till we reach C, in which case there's a force acting downwards. So that will get it back to 0. So this is the shear force diagram, which we drew without drawing any free body diagram, just using this expression. Okay, so it's up to you how you want to solve it. Some people find this one easy. Some people find the free body diagram method easier. Okay, now here, what we're going to do is we're going to use the fact that dm dx is v. In other words, if you integrate this, m2 minus m1 is v dx 1 to 2. This is the thing on the right side is actually area under px curve from 1 to 2, right? Okay, so with that, we don't really need to write any equations. We just can go through with drawing the bending moment diagram. Mx. Okay, for that, what we need to do is we clearly need the area under the curve, area in the Vx curve. So we need to peek into Vx in order to get that. Okay, so let's find the area here. So the area of a triangle is half base times height. The base here is 3.34, height is 133.75. So half base 3.34, height 133.75. This comes out to be 223.36. Okay, next we look at the area under the curve for this part. Again, half base into height, half. The base is now, this is 8. So 8 minus 3.34. Minus 3.34 space. So it's going to be half 8 minus 3.34. That's going to be the base. The height is, as you can see, it's minus 186.25. The negative sign is actually important. So when you do this math, you get 433.36 minus 433.36. 433.96 maybe. Okay. Okay, and then finally we need to compute the area of this rectangle. Okay, that's going to be this is 3 meters long and 20 meters high. So 20 times 3, which is 60. So that's plus 60. Okay, so now let's put that area under the curve to use to get the bending moment diagram. So we start off with x equals 0. You can clearly see that the moment is 0 because the only force acting at A is the 133. There's no moment. So if you take moments about A, that moment should be 0. So that's 1 point. Next, we have 133. Well, it's 223.36. So the area from A, let me call this point, I don't know, let's call that, let's say D. Okay, if this point is D, what this is saying is if you go from here to D, you should get a intercept. Well, this should be 223.75. right? Because remember, it's the area under the curve is m2 minus m1, but m1 is 0, it being point A. m2 is the one which is 223 from the area under the curve. So this is the second point. Okay, then we have area from D to this point is C is negative 433.96. Okay, so we can write MC minus MD equals dC VDX. So M at C is unknown, M at D is known, is 223.75. The area under the curve is negative 433.96. So this goes here. Okay, we see that we can solve for MC here. MC is 210.6. Okay, which gives us a new point here, negative 210.6. Okay, now the thing is we need to connect the dots. We need to connect A to 223.75 and then 210.6. Now we know that if V here is a straight line, V is proportional to X. So we have M is proportional to V dx, but V is proportional to X. So M is proportional to X dx, right? So when you take the integral, it's something like X squared divided by 2. So the M is proportional to X squared, which means it's a quadratic. So we need to draw a curve from A to D and D to C, because from A all the way to C is a straight line, which means it's a linear function of X. So I need to join this like this. Yeah. Did I make a mistake in, is the math wrong? Maybe it is 220. Yeah, 36. Yeah, you're right here. Just mistake writing the equation. 36 is right. 36 and then 36. Oh yeah, 36. I wrote incorrectly wrote there. Okay, now we have to go from C to D. Okay, we again look at the area under the curve. It's 60. So if you write the equation again, M at, I think it's the point is, oh my bad here. This should be B. Follows this. This should be B. This should be C. So I need to make a correction here. This is MB minus MD. Okay. Then this should be B to, oh, so D to B. Okay. Now, finally, we need to go to C. And so for that, we look at the area under the curve. So we have MC, which is this point, minus MB, is the area under the curve, which is 60. But MB is minus 210.6 equals 60. So you can solve for MC. Yeah, I did a mistake here. This should be. No, actually, it'll work out to be, you don't have to include the moment. Yeah. It'll actually come out to be 150. I think I made a mistake here. This should be, this is 210 somehow. Yeah, right? This is, no. There is some carryover mistake, which I did. There's a decimal place. MC comes out to be 150 actually. I think there's a problem here, which means it's probably a problem here. This might be 36. Need to check. I think it's 36. So it should always come out to be whatever that moment is, 50 at the end, yeah. Yes, right, right. Yes, this is how it should come out.